Hello students, let us start with the next chapter, that is ionic equilibria. You have studied chemical equilibrium in 11th standard. In this year, we will be studying ionic equilibrium. So what does it mean actually? The equilibrium between, so this ionic equilibria is nothing but the equilibrium, I'll be writing in short, equilibrium between ions and unionized molecules. So this is important. The equilibrium established between the ions and unionized molecules in solution. Of course, in solution. It's called ionic equilibrium. Okay. Now we will be studying 4 different types of ionic equilibria. Number 1, that is H plus and OH minus ions and unionized water molecule. So the equilibrium between H plus and OH minus ion and unionized water molecule. Number 2, that is ionization of weak acids and weak bases. This is important. Ionization of weak acids and weak bases. Number 3, that is the reaction between ions of salt and ions of water. So we'll be studying here in both the cases, here and here, we'll be studying hydrolysis also. So I'll be explaining what is hydrolysis and all in detail as we proceed further. Then the next type, that is the solid salt and its ion, ions in water. So how the equilibrium is established between in all the 4 conditions, we will be studying under this heading of ionic equilibria. Now, as we studied already in 11th standard, that is chemical equilibrium. So equilibrium is established when the reaction appears to be stopped, meaning the concentration on the left-hand side of the reaction, when it becomes equal to the concentration on the right-hand side of the equation or the chemical reaction, where you may feel that the reaction is stopped, but actually the rate of reverse reaction is equal to the rate of forward reaction. When these two rates becomes equal, the equilibrium is attained. Now, the strong electrolytes, they dissociate completely in water. Completely dissociates in water. I mean, there is no unionized part remain in water if the strong electrolyte is strong. And weak electrolytes, they dissociate partially in dilute aqueous solution. So an equilibrium is established between ions and non-ionized or unionized molecules, and the ionization reaction is represented by double arrow. So when you represent the reaction in this way between the ions and non-ionized molecule, it means that the ionization, there is a establishment of the equilibrium between ions and unionized molecule. So ions and unionized molecule, they will be appearing in case of if the electrolyte is a weak electrolyte. So we'll be more concerned about these weak electrolytes. Now, the next of all these things we will be studying, that is a basic primary things about the ionic equilibria. Now, as we proceed further, we can write as starting with degree of dissociation. So we'll discuss about this ionic equilibria in detail in case of strong acid, strong base, weak acid, and weak base, and hydrolysis and all. We should know some of the terminologies involved here. The first is degree of dissociation. And prior to this, after this, we'll be talking about the different definitions of acids and bases also. So this degree of dissociation, it is denoted by alpha, and it is defined as a fraction of, this is the fraction of total number of ions, total number of moles rather, total number of moles of electrolytes, total number of moles of electrolytes that dissociates into dissociates into ions when equilibrium is attained. Means when the reaction reaches to equilibrium. So whatever the fraction of the total number of electrolyte that dissociate into its ion, that is called as the degree of dissociation, which is denoted by alpha. Means in formula, you can write alpha, that is degree of dissociation, that is number of moles dissociated when the reaction attained equilibrium, divided by the total number of moles of electrolyte. Total number of moles. Okay. Or you can write the same thing in terms of percentage dissociation. You'll be solving the problems based on this. Percentage dissociation, it is alpha, that is degree of dissociation. When to multiply it's 100, that will give you percentage dissociation. Now, if C is the molar concentration of an electrolyte, if C is the molar concentration of an electrolyte, the equilibrium concentration of cation or anion, because any electrolyte, it will be dissociating into either in cation and anion. So the equilibrium concentration of cation or anion, it can be given by this equation alpha multiplied by C. This alpha is nothing but the degree of dissociation, and C is the molar concentration of electrolyte. And the unit for this will be moles per dm cube. So this is about the degree of dissociation and the percentage dissociation. Now instead of this, if before proceeding further, we should know what is an acid and a base. How will you define acid and base? Different theories were put forth by different scientists. So first we'll start with the Arrhenius theory of acids and bases. Acids and bases. Now, according to this theory, acid, it is a substance which contains hydrogen and gives rise to H plus ions. We know this thing, H plus ion in aqueous solution. Isn't it? Now, if you consider, we all know the hydrochloric acid, and if you prepare aqueous solution of this water is added to this, it will dissociate as H plus and chloride minus or chloride ions in aqueous medium. If you take another acid, organic acid like acetic acid, I'll put here double arrow. It means that it dissociates weakly. So CH3COO minus plus H plus. So these two ions are formed when it dissociates. Now H plus ions in water, It's hydrate in aqueous solution, and this H plus ion, it hydrates in water in aqueous solution, and it is represented as H3O plus, that is hydronium ion. So now onwards we'll be writing hydronium ion instead of H plus ion, because this H plus ion which are formed here, if you are saying that hydrochloric acid is added into water, so water is there plus H plus ion from this acid, they will combine together to form this H3O plus, what we call as the hydronium ion. Okay. Now, according to this, acid is a substance which contains hydrogen and gives rise to H plus ion. Very simple definition. Now, what is a base according to this Arrhenius theory? Base is a substance which contains OH group, and produces OH minus ions in aqueous solution. Very simple thing. For example, NaOH, it is a strong base, so it will ionize in this way. Na plus and OH minus ions will be formed. Whereas this NH4OH, which is a comparatively a weaker base, so you can put here double arrow. So NH4 plus and OH minus ions are formed. So this is a strong base, this one, and this is a weak base. Whereas here it is a strong acid, and this is your weak acid, acetic acid, it is a weaker acid. So accordingly, means the substance which contains OH group, it is a base, which contains H plus ions, that is an acid. Now, another way of defining this acids and bases, the another theory which was put forth, which is called as the Bronsted-Lowry theory. Bronsted-Lowry theory. Now, according to this theory, acid, it is a substance that donates proton. Means H plus ion to another substance. And base is a substance that accepts proton from another substance. That is a base. So from and to, and donation and acceptance. So these two words are important here. Donates to another substance and accepts from another substance. So proton acceptors are bases and proton donors are always acid, according to this concept of Bronsted-Lowry theory. For example, if you write HCl plus NH3, I'll write the simple reaction where it will react together in this way, formation of NH4 plus and chloride ion. Ammonium ion is formed and the chloride ion is also formed. This proton, it is donated and it is accepted by this ammonium molecule. Now in this above reaction, HCl and NH4. Remember here, HCl and NH4 plus. These two are the proton donors. These are proton donors, means they are having hydrogen ion in them and they have the ability to donate this proton. So these two are the proton donors. So according to the definition, proton donors, it will act as acids. Here you can see in case of this ammonium radical, this one proton extra is there. And here in case of hydrochloric acid, proton is already there. So these two are the proton there, whereas this ammonia and Cl minus, these are proton acceptors. These are proton acceptors. You can see in the reaction itself, this ammonia and accepting proton from here and getting converted into this ammonium radical. This ammonia, it is accepting proton from this hydrochloric acid and it is getting converted into ammonium radical, isn't it? And this proton acceptors and this acts as a basis here. Whereas in case of this chloride ion, it accepts a proton and it is getting converted into hydrochloric acid. Don't get confused here. Here this NH3 and Cl minus. I said here NH3 and Cl minus. These two are the proton acceptors. So proton acceptors acts as base or basis. Okay. Now if you look at this HCl and here this HCl and NH4 plus. So when I say HCl and NH4, these two are the proton donors. They can act as an acid. So you can write here as acid 1 and this is your acid 2. Okay. Now this for this case, for this one, this is your NH3. Here we are already written. These are proton acceptor acting as a base. So I can write here as a base 1 or rather base 2 and this is your base 1. So we just differentiated acids and base species from the given reaction. Now we can join them together. Now look this is when I say this is acid 1, you can link this to this base 1. Okay. And base 2, you can link up this with the acid 2. So these two pairs, hydrochloric acid and NH4, these are called as the conjugate HCl and NH4 plus or HCl and Cl minus. Remember HCl and Cl minus here. Look here. HCl and Cl minus. This is acid base conjugate pair. Okay. So I'll write here the conjugate base of bronzed lorry and it is a species found after an acid donates a proton. Means this HCl and Cl minus. So when this acid it donates a proton, chloride ion is formed. So this is your acid 1 and this is your base 1, isn't it? Same thing. It is shown here in this reaction also. This is base 1 and this is your acid 1. So the conjugate base of this hydrochloric acid, it is a chloride ion. Okay. Now for the another pair, I can write the conjugate acid of a base is the species formed after a base accepts a proton. So whatever I just said, it can be shown this way. NH3, it accepts a proton and ammonium radical is formed. So this is your base 2 and this is your acid 2. Okay, so you can see here, this is your base 2 and this is your acid 2. Don't get confused here. Always remember HCl and NH4, these two are proton donors, mean both of them will act as an acid. And NH3 and Cl minus, those are proton acceptors and they will act like a base. So look at this on the right hand side, this is your Cl minus. So Cl minus will be getting converted into its acid after accepting a proton. Means this chloride ion, you can say it as a proton acceptor. So this will be your base. Okay. NH4 plus, it has got extra proton in it. So this proton can be donated and after donation of this proton, it would be converted into NH3. Means ions which are formed on the right hand side, you will have to correlate it with the species which we wrote on the left hand side of the reaction. So those will be the conjugate acid base pair. So HCl and Cl minus, this is the conjugate acid base pair, and NH3 and NH4, these two are the conjugate acid base pair. One of them would be base and another would be an acid. So we'll have to decide them by looking at the reaction. So here NH3, in case of this NH3, it has got a lone pair. We know this. In case of ammonia molecule, it has got a lone pair on it. I'll write here. This is the ammonia molecule, tetrahedral structure. So this lone pair is present on this nitrogen and it uses it to accept a proton, and that is why this ammonia molecule, it can act as a base due to the presence of lone pair on it. Isn't it? Now this is your conjugate acid base concept. You should be very clear with this conjugate acid and base pair. I'll explain this with another example also. Proceed further. Now, if you take another example like HNO3 plus H2O. Now, by taking this example, I am trying to explain how this water molecule, it is amphoteric in nature. I mean, in one of the reaction, it acts as an acid, and in other reaction, it can act as a base also. That is why it is called as a amphoteric in nature. So these are the ions formed in these reactions. Of course, the aqueous medium is there. This is liquid. Okay. Now here HNO3, looking at this, HNO3, it donates a proton and act as an acid. So this is your acid 1. After donation of proton, it will be converted into nitrate ion. So this will be your base 1. So this is the way you decide the acid base pair. H2O here, you can write here, it is this H2O1, H2O in liquid form. On the right hand side, there is a protonium ion. So this protonium ion can donate a pair, H plus ion, and can be converted into H2O. So this is a proton acceptor species. So you can write here base 2, and this will be your acid 2. Isn't it? So these two are the conjugate acid base pairs in them. Okay. So H2O accepts the proton from HNO3. From here, it accepts a proton to form protonium ion. Here this H2O, it accepts a proton from here and getting converted into protonium ion. Now here, you can say here this water molecule, in this above reaction, it is acts as a base in this particular case, in this above reaction. So the reaction highly favors the formation of products. So the reaction arrow is drawn only to the right. And because since this is a strong acid, so whenever it is a strong electrolyte, only forward reaction is favorable or the possible. So only one arrow is shown here. So where in this above reaction, water molecule, it acts as a base. Now I'll take another example where this water molecule, it can act as an acid also. For example, in case of NH3 plus H2O, it is in liquid form. So it is a forward reaction and reverse reaction also. So it is getting converted into ammonium ion plus OH minus ion. Isn't that it? Very simple thing. And you can just locate the acid base pairs now. This ammonia, it is getting converted into NH4 plus here. These two things. Now on acceptance of this means it is accepting a proton. So you can say it as a base. And this NH4 plus, it can donate a proton. So you can label it as an acid. So this H2O here, it is donating one of its proton to NH3. This H2O water molecule, it is donating one of its proton to this ammonia molecule. And after losing a proton, H2O, it is getting converted into OH minus ions. So since this water molecule, it is losing a proton here. So you can write it can act as an acid here. And this you can write as a base. So NH3 accepts a proton from water to form NH4 plus, and ammonia here acting as a base. Water here it is acting as an acid because proton when according to this definition of this Bronsted Lordy, that is a substance that donates a proton. It is to the another substance. It can be defined as an acid. So this water here it is losing a proton and getting converted into OH minus. So it can act as an acid here. So you can write here as a write as starting from acid 1. So this will be your conjugate base, that is base 1. If you write this as acid 2, so that it will be base 2. So these are the two conjugate acid base pairs. Isn't it? Now you can see here clearly in this particular reaction, water molecule it is acting as a base, and in this reaction, the second reaction, this one, H2O act as an acid. And this is actually possible because this ammonia molecule, it has got a lone pair on it. Okay, and due to presence of this lone pair, it is acting as a base. So these two reactions clearly shows that water is amphoteric in nature. Means in some of the reaction, you will find that water molecule is acting like an acid, and in some of the reaction, it might act like as a base also. This you can see clearly in case of electrochemistry also. If you go through the electrochemical series, you will find the same thing. Now the next thing and the lastly, that is a Lewis theory. How will you define acid and base according to this Lewis theory? So acid is a substance that accepts a share in an electron pair. Means acids are those which accepts an electron pair. Isn't it? And bases, I'll write here, acids that accepts a share in an electron pair. So now we are defining the acids and bases on the basis of electrons. And bases are the species that donates a share in an electron pair. Okay. Now, for example, I can explain this with very simple reaction like this. H plus and this ammonia molecule. Ammonia, as I already told that, and you all know, ammonia, it has got a lone pair. So this lone pair of electron can be donated to this proton, and the coordinate bond is formed. That is nothing but a formation of ammonium radical. So this type of bond is formed, which is called as the coordinate bond, or the dative bond is formed. So in this reaction, it is acting as an acid. It is behaving like a base. Okay. Now another example you can quote for this BF3, which is an electron deficient species. BF3. It reacts with this same ammonia molecule. So this electron pair can be donated to this boron, and the product you can write in this way, BF3, and the dative bond is formed between these. So in this case, this is a base and it is an acid. So according to Lewis, acid is a species that accepts a electron pair, and base is a species that donates a electron pair. Means acids donate. I'll write in short for your convenience only. Acids donate proton. Means if they are donating proton, what should they accept? They should accept electron, isn't it? Now bases donate electron. So if they are donating electron, what should they accept? Bases accept proton. So in short, you can summarize the whole theories Acid donates proton, acid accepts electron. Bases donate electron, bases accept proton. So this is the simplest way you can define acid and base. Okay, so in the next lecture, we'll talk about the dissociation constant of weak acids and weak bases. Thank you.